Thanking the Bangalore Science Forum for inviting me and giving this opportunity to come and meet such a diverse group of people from plus 2 till till at such levels that I have hesitation to even speak, because probably the wisdom that is there in this hall is far beyond compared to what I could give. So I would try to make some very general statements before entering into anything else that I do. It's a national college, and the name certainly was there even before we became a nation, I was told. This is remarkable. So nobody can take away that credit from National College. And also to keep this tradition of giving 30 days of a science mela, if that is the way to put it, intense mela that is, for 38 years, this is unprecedented. And do that in a college which only recently got many postgraduate degree programs. For a long time it was the school, then the graduate program, and only now the postgraduate program, a few years. And this is indeed even more remarkable. In fact, when I was walking in, I saw a student who said, "I just listened to you 3-4 days ago," and that was true. There was the Inspire Science Camp, and one student from this particular campus was there, and he is possibly still here. And today, yes, he is still there. That was nice. I was at that time talking only about the importance of selecting something that one would like to do for the whole lifetime, so that we are not forced to do things that we do not want to do, forced by either parents or classmates or society at large. If you like to do something, and if you can succeed doing that for the whole life, there's nothing like it. And that's really what we should try to get. It may be a little late, one can say, when somebody says, "Oh, I have already started doing a graduation in whatever subject." It is not late, because in today's papers we would have learned about, in the Hindu it was, about Edward Witten. In Edward Witten talking about string theory and many other things in science. See, normally when we talk about things, like Professor Abhirao would talk about National College and the institute that he has done his PhD. Professor Anasuya will possibly talk about Indian Institute of Science, every other moment that he gets. For me, I talk about IIT Kanpur, and I talk about Princeton University, and Edward Witten and I joined together in 1973 for PhD at Princeton. I joined in chemistry, he joined in physics, and we stayed in a hostel which is called Graduate College. Strangely, like you would have seen it in Feynman's book, Graduate College is the name given to the hostel of the PhD students. And nothing surprising except that Edmonton came there after doing history. Largely history courses in BA. He had taken some physics courses, and he felt he should actually shift. So he came to join physics department. With some courses he has already taken in physics, but largely in history, and had an inherent interest. And he went on to write the so-called preliminary exams and comprehensive exam on his first year itself, and passed them all. And it looked as though he was an unusual student right then, another shy person. So I say this because he became famous, world famous, not so much for string theory initially, but for the mathematics that he developed for formulating string theory was so much of a high quality that the mathematicians gave him a Fields Medal in mathematics, even though he was a student of theoretical physics. So he became, household world actually outside physics in mathematics through Fields Medal. He may get a Nobel Prize, but as we read in today's paper, string theory, predictions of string theory might take a few years before anything could be really discovered. I say all this because it is never late to switch fields. If we have a will, there is a way. And I understand from the principal as well as from Professor Ramon that next year onwards, you will have an autonomous nature that allows you to formulate your own courses and even an open-ended course structure so that people can come and start a degree program and at the end of first year decide what is going to be the major. I hope it happens. At least the possibility might open up from next year. This is what I understand for the National College, which is really good if it actually happens. The problem with the current system is that we decide, okay, if you want to take mathematics, we have the ancillary subjects, physics and chemistry. If you ask them, look, I want to take biology, mathematics and physics with biology, there is a reluctance. And that too, if you want to select it, we have to do this right at the beginning. There is no opportunity to come in and start studying different subjects and decide what is to be selected. So hopefully we will come to a stage where we will really learn what we like to learn all through. It is difficult difficult to predict when it will come through, but that's the aim. We can of course ask why we came to this stage where we would have this compartmentalized programs, where we do not have a choice. See, it's a little of a history that we have to talk about. Because let's go back to the beginning of civilization. Right? When we didn't know anything, and human civilization began with people asking questions, and everybody asked everything, so to speak. Whether it is Indian history or the Greek history or Chinese history, initial stages, people asked everything. Economics or sciences, natural sciences, or these were observations and questions. And even later on, we had, for example, Newton, a mathematician. Again, today's Hindu, the interview with Dept talks about this. People did everything. Galileo didn't have any reason to say that I will do only physics. In fact, physics in that world didn't even exist. So there's no problem. But as we progressed, there were compartmentalization. There were mathematics and the natural sciences. It became physics, chemistry, biology, which is still acceptable. Then chemists, for example, became inorganic chemists, physical chemists, organic chemists, and then even without stopping further, they went on to divide further, physical organic chemistry and analytical and many other. And we specialized and specialized and specialized. In the beginning of last century, or I would say 150 years ago, these influence of the specializations also was reflected in the university education in Europe. And they had these compartmentalized BSc or bachelor's programs, physics, mathematics, some related subjects were put in as a convenient aspect. Europe left it already more than 100 years ago. But what was started those times in India, we are still holding on. What we have is something totally artificial. This doesn't exist anywhere else. It's just that we haven't thrown it away. And slowly we are trying to change. And National College, I hope, will be the leader in this process. In a small way, the new ICERs have started this. The Indian Institute of Science Education Research, where you join and take several courses and then decide. Indian Institute of Science started a 4-year degree program 4 years ago and had this option. But it was a very limited one because we don't have humanities and social sciences and performing arts and fine arts and communication and so on. Everything has to be there. And National College has a lot of it, but not everything. But at least there is this option possible. Somebody taking a major finally in mathematics with a minor in literature or any other subjects. This realization has come now that if you want to do something very deep these days, you need to know not just one area of one narrow branch of an area. We would go beyond. People who would look at all of chemistry would do better chemistry. People who can understand physics and chemistry would go even beyond. or physics and biology could see further. See, the examples that I take are from people and places that I know. So I come back to Princeton again. See, when I was a graduate student, there was an undergraduate student in mathematics with the name Eric Lander. Eric Lander went on to do PhD in mathematics. He did work in mathematics for a few more years. But then, there was this expansion of large data, large volume data that started along with genomics, which the sequences of biopolymers. Such large data, he was thinking always that, look, biologists cannot handle it, I should get in. And he did. With the result that when MIT started the so-called Whitehead Institute of Genomics, the director was Eric Lander, the first director of this institute, a mathematician turned biologist. Right? So there is nothing that prevents people going from one area to another. In other words, if you learn at a level that is a little higher and is open, you can actually branch in whichever way you want. But even more interesting is that this, this early questions or ability to ask questions in different areas, that is with us when we are very young. When we are in +2, we can ask a question that is really science as a whole. The moment you finish an MSc in physics, we do not ask a question that spans all of science. We lose that ability. And the moment we start doing PhD, it's gone totally. Because you then concentrate on one problem, and all the things that we think about will be about that problem. Even after PhD, you tend to have that problem. And it has its consequences. So we have to really curtail this. In addition to curtailing the general tendency to go into a program that gives, within quotes, in the minds of everybody, jobs immediately. I'm not really coming to my talk, but it doesn't matter. What I really have to say about my science is not as important as about the general things that I might tell you, because those are not usually written down. What I have to tell you about my science are published mostly, so it's not so really. But let me tell again. About 2 or 3 years ago, Chris Gopalakrishnan was in ISET Trivandrum, because we have the College of Engineering Technology campus coexisting with the engineering institution. So he came and he was saying that he wanted quantum cryptography, and there is a talk soon, right? He wanted a group in Infosys brought up in quantum cryptography. The reason is that the current level of encapsulation of data is not good enough, because with a supercomputer it is possible to break anything in 2 weeks' time if you have a supercomputer. But if you have encryption using quantum cryptography, it might take probably 8 months of the current level of computers, or 10 months. So there is a chance. But then he wanted about 20 or 30 people with MSc in mathematics. And he said in Bangalore, you cannot get 20 or 30 people with MSc in mathematics. Because even in BSc in mathematics, there are people. This is what he was telling at that time. Because people who are actually in mathematics are in mathematics because they didn't get something else that they wanted. So it was not easy to get 20 or 30 people with MSc in mathematics. Not surprising. I was told many colleges have closed down mathematics and physics and so on in BSc level. This is something that is worrying. Statistically, it doesn't sound to reason that 90% of the graduates of +2 students, 90% of them would either be interested in engineering or in medicine. It just doesn't sound statistically correct. There's something else that is forcing. The consequences are seen. I am not trying to advocate that one should not go into engineering. If one has interest, one should all the way go. But one should think about it a little longer. And I say this because at least these thoughts might be already existing in the minds of viewers, but it's possible to articulate this to a few more people. Now I come to the part which I wanted to But importance of early questions in science. I really would, I will skip this. I think I will just concentrate on the last part. So just as I said, when civilizations were young, questions were more general. Just the same way, when we are young, our thought processes are less influenced by what is already known. Even philosophy has not influenced us. So it is good to ask questions when one could ask them when one is very young. And those questions usually are very general. Now, I tend to ask questions by force to make it more general. And when I say general questions, it is easy to go back and see general questions. This is a page from the notebook of Mendel's when he was trying to figure out what could be the way to organize elements. When he was getting the 59 elements were known, when he thought there has to be an order for all these elements. And he was trying to figure out, cutting, pasting here, there and all, correcting this, making, there is of course carbon, nitrogen, oxygen, fluorine, beryllium, something is missing here, and he looked at the aluminum after bonding, but he was looking at something else that was not fitting. There is this process of finding something new from a set of data. This is important. Of course, we can say we cannot now rediscover the periodic table. That is true, because he published it in 1869. This is how it was first published. We have now the modern one. There is absolutely no problem. But this was science at its best. It didn't involve really mathematics or any complex operations of any kind. Just looking at the properties to the extent that it is available. This is before electrons. Electron was not discovered. Right? So we are talking about very elementary knowledge of elements. Now, I want to bring in one early question that I had asked in a class. I was in my first year BSc. This was at the University College in Trivandrum. I asked this question because I was a really good teacher in chemistry. He was describing something that all of you know. See, we have tetrahedral carbon. If we put 6 of them, we can make cyclohexane. Each of these ends have 2 hydrogens, which I haven't shown. But if you consider putting them together, you can construct diamond. Right? Of course, there are different ways of representing. But if you can just connect each carbon to 4 other carbons in tetrahedral way and then connect it, you have diamond. This was a great discovery. 1874 this was proposed. There was always a doubt about this in the minds of physical chemists and physicists. In fact, when Bragg discovered X-ray diffraction, one of the first crystals that he put in was a diamond crystal. And found, yes, this is true. Right? In fact, we had the Huckel rule aromaticity for benzene 6 pi electron. That's also well known. Our class, incidentally, this is taught in +2 nowadays. 11th and 12th class already this is available. And even earlier, I was being taught this only in the first year BSc. You see this connection as well. When I was being taught, this was graphite. Now you have individual sheets, graphene, right? A very attractive one. But you see the connection. So this structural connection was taught to us in BSc. And for some reason, in this class, I happened to ask this question. Is there something like this for the next element, boron? We have this icosahedral borane which was already known. We had this textbook even in the 60s, Cotton and Wilkinson, Inorganic Chemistry. A classic book of 1960s at that time. It had this B12, H12, 2 minus as an icosahedral arrangement. Is there anything that we can see whether this one connecting to elemental boron? It's a question that was asked without much thinking. Of course, one can say, okay, this was asked in 68, 69. There was no immediate answer. Teacher didn't know what the structure of elemental boron was. It was not there in the textbooks. All that was there in the textbook was B12, H12, 2 minus. I went to IIT Kanpur and there was Professor B.T. Manoharan at that time. He is retired now. He went to IIT Madras after after my 2-3 years there. And in the course, he was teaching inorganic chemistry course at Kanpur. He had all these projects. He had to write an essay, and I took again, something connected with the boron when the opportunity came. The answer was not still there. In Princeton, for PhD final oral examination, you do not have to defend the thesis. Because thesis is monitored by a committee, research supervisor and 2 others continually. And often most of it is published anyway. And so the thesis doesn't require any defense. But they wanted, along with the thesis, 3 research proposals which are not connected with the thesis to be given along with the thesis. And these 3 research proposals has to be defended, saying that these are provable proposals. So I gave 3 proposals. One of them again was connected with boron. Because I thought somehow I have to stay on with it. I didn't want to leave this question. Even though I didn't work on this, I didn't get an answer. I talked about, B12, X12, 2 minus, and the neutral one had 2 carbons. B minus replaced by carbon, which will be isoelectronic change. I tried to formulate these questions a little bit more. These questions did not have an answer for the next 30 years. I didn't leave this question, it was always in the back of my mind. I did other things, because if I didn't do other things, I wouldn't get a job, right? So even though this early question was in the mind, I kept it going. And you can of course now ask all kinds of things. Why boron? I can talk about various reasons why boron is. We have all these corrosive classes. We have many other reasons why boron, materials, this, that, and other. There are enough reasons to study boron. There is boron nitride. There is of course many of these cosmetics. There is boron neutron capture therapy for cancer. There are a lot of reasons why we should worry about. In fact, boron even got some Nobel prizes. Lipscomb got a Nobel Prize in boranes. There is a connection. See, the person with whom I worked for my postdoctoral work did his PhD with Lipscomb, right? And it is kind of amazing because Lipscomb got the Nobel Prize in '76, and the person with whom I worked, Rolf Hoffman, got his Nobel Prize in 1981. Just 5 years after this. We say that Lipscomb went down after 1976, he shifted the area, he left boron and went to macromolecular crystallography. And there was a speculation that he might get a second Nobel Prize, but he passed away before any of that happened. But you can't blame him if he thought like that, because his PhD supervisor had 2 Nobel Prizes. That was Linus Pauling. One was in chemistry, but the other was in peace. H.C. Brown got a Nobel Prize for what related to boron, but it was hydroboration, not elemental boron. And I want to say, though I was worrying about it, I did other things. And many other things. I am not going to talk about, what research I have done. It is not so very important. Let me skip. But I want to show this slide. See, normally this is what happens. We try to join for PhD. And when we have all this idea as a young student, maybe, MSc student, or I will do whatever I want to do research, and we join and we say, I am going to do research whatever my professor wants. And then you get a job and you are not sure whether you will get a permanent job, so you are really rushing to see, I am going to do research whatever my tenure committee, the committee that will give me a permanent job, thinks it is appropriate. You actually get a final job and then you think, all right, I have to have money. So I have to write proposals. If nano science is the hot thing and that is what is going to give me money, I will do nano science. I will forget what I wanted. Right? And finally, when you think you are free to do it, virgin is today. So what I would like to say is that it may not be this way. You should hold on to some questions at least. Somewhere along this way you will get the chance. and ask questions now. I am now talking to the first year BSc and second year BSc, third year BSc, first year MSc students. Ask as many questions. Some of those questions will be very important. Some of them would have been solved already. Doesn't matter. Find out whether it is solved. Right? Some of them would be trivial that even textbooks have it. Doesn't matter. But some, I am sure, will be so difficult that nobody even thought of it, or even if they did, there is no answer. In fact, I come back to today's Hindu. Again, the last statement of Edward Witten in the Hindu interview today. The last statement he said is that the message to the young students is the following. There is more science to be discovered than all that is already known. This is exactly the statement. There is more science to be discovered now than all that is already known. Right? So there is a lot to know, a lot to do. And those questions are better asked when one is not highly specialized. So that's why I gave the title, Importance of Early Questions in Science. It is not just questions that are asked by scientists in early times. It is the kind of questions that a beginner in science can ask. We should really be asking. In fact, when this was a slightly modified or different version of it was presented in the science Inspire Science program, I had in the first slide. Let me go back. Some of you will recognize this. This is in Western Ghats. Every 12 years there is a flower that blooms. Every 12 years there is a flower that blooms, and it blooms such that the whole area becomes of this color. And color is not produced so very. I mean, it's a remarkable scene. And one of the students asked this question, why every 12 years? Why not 11 years or 13 years, 6 years? There are partial answers to this, but only partial answers. Very difficult question. Because molecular biology, genetics, ecology, environment, everything has to come together to give an exact answer to this. It has not been answered fully. But it is not the kind of question that if I am doing PhD in let's say, research for diabetics or a specific enzyme modeling or in molecular biophysics, I will not ask this question. But if you are a first year BSc student and going on a tour, you will ask this question. You should ask this question. Right? This is the importance of asking questions. So, anywhere, I mean, this was not a question that I had planned, but in the science camp, Inspire camp, the +2 students asked, and some of the people there had partial answers, but they also knew that the current level of understanding is partial. There are people working in plant genetics, plus all the other branches together working on this. In fact, even thinking, can we make this 6 years, 5 years, 10 years at will by whatever tricks that are needed. Well, I'm really not so much worried about whether I will talk to you about what I wanted to talk, because it's not so very important specifically, because it's a rather complex topic. If it were not a very complex topic, I had the good fortune that for 30 years nobody actually found anything about this connection, right? But it is general enough that once I found it, just as the connection between methane and diamond and benzene and graphite are in textbooks, the connection between B12H2O2- and elemental boron allotropes are already in textbooks, not in as great detail, but it is coming in. And it has become a material that people teach in many advanced inorganic chemistry courses across the world. But let me go back to this. This is something that you have already seen. Those who have done inorganic chemistry only will know. But this is polyhedral molecules, B12H2O2- and so on, plenty of them. Suddenly I have lots of pictures here. I have written that plenty of things to come, structures from modern chemistry. We had talked about B12, S12, 2 minus, which is an icosahedron. And the actual structure of elemental boron, the most stable allotrope, is a very complex one. So my attempt here will be at least to describe it and not really succeed perhaps in showing how this connection comes in. The benzene to naphthalene to anthracene to graphite connection. How we establish this. It is not clear whether I could reach that mark. I could stop anytime you feel that, oh, enough is enough. This guy has got us. Okay? So feel free to stop me. Otherwise there is a problem. Just as many of you are teachers and we have tendency to keep going. Right? So be bold. If you want to ask some questions, anytime in between, absolutely is fine. You know, that's one indication that yes, probably you should stop. Right? I tell this in advance to Persona Rao. Do not be polite and let this go on and on. Because there is this tendency for teachers to keep going. Now, there's one Professor Wade who has formulated what is called Wade's rule. Anyone who has done MSc in inorganic chemistry would already know. What he has done is that if you have an icosahedral or a polyhedral borane, a polyhedron where all the faces are triangular ones, he has a rule to say that there should be -2 charge if it is like this, and if it is having one vertex less, it should be instead of n+1, n is the number of vertices. There is a way to calculate this and justify this rule. Now, this has been the backbone for polyhedral molecules of boron kind. Whether it is B12, H12, 2 minus, B11, H11, 2 minus, B6, H6, 2 minus, they are all known. It is also known that B12, H12, 2 minus is the most stable compared to all the other polyhedral boranes, experimentally known. There is a theoretical explanation why this is the most stable one, but I will go to that because that will again another half an hour at least. But it is something like benzene. When you consider aromatic compounds, benzene is the most aromatic system. In organic chemistry, if you want to take the most stable aromatic compound, benzene is the most stable aromatic compound. In inorganic chemistry, just the same way, B12, H2, 2 minus is the most stable one. So it is natural to anticipate that just as benzene have been the building block to give the most stable allotrope of elemental carbon, that is graphite, you should anticipate B12, H12, 2 minus should be the building block for generating the most stable allotrope of elemental boron. Just a one-to-one correlation between benzene to graphite, there should be something B12, H12, 2 minus to beta rhombohedral boron. Beta rhombohedral boron is the most stable allotrope. Now, I will skip this and go to the way to generate. Now, I am just trying to describe the best structure for beta rhombohedral boron that is known. An idealized structure. The real structure has more complexities. And with this idealized structure description, I will stop because the process of solving this required a few more things than what we normally think about. Here is an icosahedron. Ideally, if icosahedron is the most stable arrangement, we should have icosahedron for 12 of these vertices. See, icosahedron has 12 vertices. How is it 12? This is a pentagonal pyramid. This is a pentagonal pyramid from the bottom side. These two together we have 6 plus 6, 12 atoms. If we have one vertex having another B12, like that 12 vertices to B12, that would be ideal way, except it does not form a translational symmetry based space filling model. Instead, elemental boron has found a way, it takes half of the icosahedron. So there is an icosahedron and half of an icosahedron. There is icosahedra, 12 of these around half icosahedra. Now half icosahedra is a 5 membered ring and an atom at the bottom. A 5 membered ring, there are 12 of them. And 12 5 membered rings around one, there is something unusual. C60 we know. 12 5 membered rings. Now here we have a B12 and around it 12 pentagonal pyramids. It means that 12 pentagons, and below each pentagon we have an element. Right? That's all. So it is as if it is like fullerene, this fragment. Except this is a fullerene made of B60, right? 12 5-membered ring. So B60, except below each 5-membered ring there is one corner, right? And 12 of these. And so 60 plus 12, that is 72, plus another 12 which is the inside icosahedral. So 84. So this B84, I can represent it like this. B84 is one building block, and it is connected such that you generate more of the same. So the B84 kind of unit, which has the overall structure of C60 in terms of its symmetry, is already present in beta-rhombohedral boron much before C60 was discovered. Right? So it is not as though the structure B84, C60 is such a novel one. It had its origins already in beta-rhombohedral boron. Now, the attempt will be to generate more of icosahedra from this, and one way is to just put two of them together. If you put two of these together, if there is a pentagonal pyramid, there is another pentagonal pyramid, these two can together become another icosahedral. So this is the way to kind of follow that through, and you find that this is a huge structure. You can bring only 6 of these around one of them, which means that out of the 12 D12s, 12 5-membered rings, only 6 can get to this. Now it is possible to manipulate the structure if we know where we are going by rules to connect them with the additional atoms. It's a very complex unit set, 105 atoms, and so 84, you have still more atoms. So there is a beaten unit which can be put on the top, then you have another icosahedra coming in. You can have one more of B84 around these two, so a structure like this. This is a beaten, one B84, another B84, and third B84. Now, to get the electron count, you see already it is becoming more complex. I will not, stress your thoughts a lot more. But to say that the actual structure is like two of these together connected to a single atom. So already you see it is becoming more complex. I will stop at this stage and say that yes, these are actual B84 units. I have given this B84 as a pair, and a smaller one as B10. And these units like a B84, another B84, a third B84 and a B10 connected to one boron atom. Right? That's really the unit cell description. Very complex indeed. Everything here we can understand through Wade's rule, except a pattern of this kind that is available. For this we have to do something very different, and I will come to this. Husserl rule, we have the current crystal pi electron rule. Chemists would know 6 pi electrons, 10 pi electrons, and so on. We have to get a new rule which will connect B12 H12 2 minus to B20 H16 to H16 to B30 H24 and so on. This particular process of finding the electron count, this was something that we had no choice but to discover, because that's the only way we can justify the structure of beta-rhombohedral boron. So after having seen the structure of beta-rhombohedral boron, we had to go back and formulate an electron counting rule. Now I will not really spend a whole lot of time on this, but to say that questions of this kind is as if we are rediscovering anthracene and phenanthrene. Naphthalene, benzene, naphthalene and anthracene. Naphthalene has no other aromatic isomer, but phenanthrene, anthracene and phenanthrene are isomers. Right? Similarly, we could have isomers of the borane kind, three-dimensional ones, where we have 3 polyhedra, not 6-membered rings. So there is a parallel chemistry that is possible. Right? It is not clear how many of them are known, but when we look through, we find that B20H16 first number of this was synthesized 50 years ago by Lipscomb, the one who got a Nobel Prize for it. But his Nobel Prize was for general bonding, but not for this compound. It so happened that he accidentally got this compound and he felt something very abnormal. He got an X-ray structure, the structure was characterized, but all the compounds so far had only one polyhedral trap. And he thought this is an abnormality. He left this chemistry, he didn't do anything with it, unfortunately. If he had actually pursued this path, he would have been the one to discover this electron coupling group and to connect elemental boron to B12S12, the one fragment. But he didn't. It was not even necessary for him to do this to get a Nobel Prize anyway, because there was so much of boron chemistry that he had done. Right? Now, we have this new rule which kind of explained, like one molecule leading to all kinds of other things. And a lot of it is known in literature, but we could kind of justify all of these kinds of arrangements. I would rather stop at this stage and see what your reactions are. What part of it, of what I said in the last several minutes, I should concentrate on, or leave it open, ask any question, so that I would be glad to say that I do not know, if I don't know. Anything, even things that I never mentioned.
So just give me formal vote of thanks to it,
Yes.
or to allow for the discussion.
Okay. Alright, then I stop at this stage. In that case, let me give my thanks first.
I will allow them to ask questions.
Well, I have too many things, obviously, right? I have to keep moving so quickly. Well, I have a summary slide which gives only these. This part I did talk about, how to make fluorines out of boron. I did not talk about it, but only structures. It will take not longer. I would tag the Bangalore Science Forum. Of course, all these others paid for what I do. Right? And I started with some vague ideas, and I had lots of good students who gave definite names to my vague thoughts. And they were there at the University of Hyderabad, Institute of Science, Isaac Trivandrum's, back to Institute of Science. So I had all this benefit, and I also had the great fortune to be a faculty member here. Indian Institute of Science is perhaps the best institute in the country. One is free to do what one wants to do, and that makes one free to think, to experiment, to start a course. Like I teach third year BSc students. We call it 4-year BS program. I teach the third year of that program, Inorganic Chemistry of the main group. And I said it has to be different. If you are teaching in Indian Institute of Science, an undergraduate program has to be different. So my course is different in the following. Normally students complain, I have forgotten this formula, that equation, and I couldn't answer this question. Right? I said, okay, our exams will be where you can bring all your class notes, everything that you have written down, everything, anything that you have written down, you can bring. You cannot bring textbooks, but you can write down everything. You can bring it. Then they said, oh, we don't have enough time in the exam. I said, okay, our exams will start at 6:30 in the evening. You can go as long as you want. So, last 2 years I have taught this course. Every exam started at 6:30 in the evening with all the notes that is in hand. Right? And it is a change. It is a challenge. It is a challenge to make the question paper. Because I don't want, it's very difficult when you have everything that is said in the class with them and they have infinite time almost. In fact, the last student left at 11 in the night in the last exam. But there is something very interesting. Despite my every attempt, if I take all the correct answers of every student, 100% of the questions were answered. And the highest score was 70 out of 100. Right? So there is something different, and they are, they are saying that yes, to the junior batch, they are not very, if this option is given, take it. Because after first year I thought nobody will again agree. But second year they all wanted it, in this particular course. So this is, I really thank Indian Institute of Science, and of course I thank all of you for listening so patiently for so long. Thank you.